Welcome back. Now, having sussed out all of molecular geometry, we can finally examine polarity. And so remember that polarity, as you'll recall, follows a flowchart. It needs polar bonds that don't cancel. So it needs to have some sort of broken symmetry. One way to think about that is to realize that broken symmetry means A, B, X if it has no non-bonding pairs and the B are all the same, then it's nicely symmetrical. So CH4 had no non-bonding pairs and B is all hydrogen, so no broken symmetry. No broken symmetry, nonpolar. Whereas if you have CHCl3, okay, that's chloroform or trichloromethane. Now you look at it, you have hydrogen up here, and then you have 3 chlorines down below. It's no longer symmetrical. Okay? It's got a broken symmetry. Okay? The 4 things it's bound to are no longer all the same. So it doesn't have any non-bonding pairs, but the B are not all the same. So that will be polar. Now, having non-bonding pairs and having different doulalies, different atoms bound to the central atom, doesn't always make it polar, but it often does. So we look at, for example, water. Water, as you'll recall, has this bent shape. Okay? So it has non-bonding pairs. It is polar. Okay? That it gave it a broken symmetry. Okay? It's bent like that. Okay? Similarly, ammonia has that trigonal pyramidal shape. Nitrogen up top, bound to 3 hydrogens down below, and then a non-bonding pair. Okay? It has, that trigonal pyramidal. Ammonia is also polar. We can see some examples where non-bonding pairs will not make it polar. If we look at, say, what was our trigonal bipyramidal example? Trigonal bipyramidal is the one that's always messing with things. Trigonal bipyramidal is going to add up to be polar in many cases, but not always. So, xenon difluoride is going to be, let's see, that was, well, we don't need to draw that. Again, we just know that it's linear with 3 non-bonding pairs. Okay? So even though it has non-bonding pairs, because it's nicely linear, these fluorines still cancel each other out, sort of like carbon dioxide did. Okay? So it's still a nice, perfectly balanced tug of war, so it's nonpolar. So you should still draw the molecule out just to be safe. Because similarly, xenon tetrafluoride was our square planar molecule. And that was xenon at the center of a square with fluorine at each corner. Now it's a 4-way tug of war that is perfectly balanced. So xenon tetrafluoride is also nonpolar. So you should still draw out the molecule. You should still find the molecular geometry just to be on the safe side. Because until you've had a lot of practice, you're not going to be able to sort of work out the molecular geometry really, really fast just by looking at the formula. The safest way to do it, draw out the molecular geometry. Okay, so formula will get you to molecular geometry, will get you to polarity. So polarity, you need that broken symmetry. And here, for these two, even though they have non-bonding pairs, they still have symmetry. The fluorines still cancel one another out. The broken symmetry is what does it, not non-bonding pairs. Okay. Now, if it were, say, xenon, fluorine, and iodine bound together, That would get you a linear molecule with fluorine on one side, iodine on the other. And that would be polar, because fluorine is more electronegative than iodine, so this would have a dipole moment, a net dipole moment in that direction. Similarly, xenon, difluoride, diiodide would be, xenon with iodines to one side, fluorines in the other, and so it would also have a dipole moment toward the fluorines. So having different stuff bound to the middle atom will often, again, not always, but often, give you a polar molecule. It would be fairly rare, I think, for different atoms to give you a nonpolar molecule. I could imagine, for example, something like, I'm just winging it now, so I don't know if this could ever exist. I don't know if it even has the right number of electrons to do this. But I could imagine something like this being nonpolar. So always, always, always draw it out. If you see different things around the central atom, it should be polar, not necessarily. Let's go ahead and look back at those organic molecules. Okay. So I'm not loving this orange. Let's put it back to red. So methane, CH4, CHHH. This guy is going to be nonpolar. It's got, the four atoms are all the same. It's got no non-bonding pairs. It's fully symmetrical. Nothing to it. What about ethane? That's a TH. So ethane was C2H6. Now we're looking at extended geometries. And recall, ethane looks like this. It's got two tetrahedra sort of joined at the head. Is this polar or nonpolar? That is a little bit more difficult to work out just by looking at it. You need to be able to do some sort of nasty three-dimensional math. But what you find is that, a geometry like this is still symmetric. Basically, when you have an organic molecule like ethane or propane or butane, where it's nothing but carbon and hydrogen, it's going to be nonpolar. It will not be polar. Okay? So these simple alkanes, the methane, ethane, butane, and so on, they are all nonpolar. They are all insoluble in water. Okay? These are the oils, and oil does not mix with water. So maybe that is a way for you to remember that. Then we look at ethanol. Okay. Ethanol is the C2H5OH, or CHHH, CHHOH. Now we've got a different situation. We've got this hydroxide group, and oxygen is really, really strongly polar, whereas, carbon and hydrogen, they have about the same electronegativity. It's about, I believe, 2.1 and 2.4. They're about the same, but oxygen is much higher. Oxygen is much more electronegative than carbon, so there is a strong dipole moment there. Okay, so ethanol is polar. And so ethanol is soluble in water, and you have to separate them not just by pouring the oil off, you have to distill it. Okay? And that's why ethanol is soluble. It's because it has this strongly polar, what's called hydroxide or hydroxyl group. And that's important to organic chemistry, which we don't cover much this term. We'll cover it a little bit more in the second semester. And just to continue the trend, we'll look at the vinegar, or ethanoic acid. It is CH3COOH, which you might recall was C double bonded to O, bonded to OH, and then CH3. And of course, vinegar is entirely soluble in water because you have a nice dipole moment here, a nice dipole moment there, and then nothing over on this side. So very strongly polar in this direction. Okay, so that is what you're looking for to determine polarity. Remember that you're looking for broken symmetry. And symmetry can be broken either by non-bonding pairs or by A, B, C, if you have multiple things, different things, bound to the central atom. So that does it for talking about polarity, and we will now move on to intermolecular forces. So intermolecular forces are talking about the interactions between molecules. Okay? And this is why solids and liquids exist. So, for example, here you have a water molecule, an oxygen bound to 2 hydrogens. And here you have another water molecule, oxygen bound to 2 hydrogens. And you'll recall that this has a negative charge and these have positive charges. Oxygen is negative, hydrogen is positive. So when you have molecules of water close to one another, you have a positive charge here, a negative charge here, opposites attract. Okay? And that is more than anything why we care about polarity. Polarity explains why molecules interact differently with one another, when they have these different structures. Water has a very, very high boiling point for its size because of the strength of this interaction. So in fact, we can look at various kinds of non-bonding interactions, as they're called, and compare them to one another. Okay? So what I just showed you was an example of a dipole interaction, specifically a hydrogen bonding interaction. So let me go ahead and write these out. So you can have, for your dipole interactions, you can have hydrogen bonding. Hydrogen bonding is the strongest of the non-bonding interactions. Okay? So this is not an actual chemical bond. It's a non-bonding interaction. It's an intermolecular force. It happens between molecules, but it is very strong. And that happens when you have hydrogen bound to either nitrogen, oxygen, or fluorine. So if you see hydrogen bound to any of those three, then you know the potential for hydrogen bonds exist. Okay? And you see a hydrogen bond over here with oxygen and hydrogen. So water forms lots and lots of hydrogen bonds. That's why it has such strong intermolecular forces. The other two, you can have a dipole interacting with another dipole, a different dipole, which isn't, if it isn't a hydrogen bond. So, for example, you could get, say, hydrogen chloride interacting with carbon monoxide. Okay? These are both polar molecules. They will interact with one another. Okay? The positive carbon, the negative oxygen, and you have positive hydrogen with the negative chlorine. And these two molecules will interact with one another. They'll mix more readily than a dipole would with a nonpolar molecule. You can also get dipole ion interactions. So, for example, water is a dipole and table salt is an ion. This is why salts dissolve so readily in water. It's because, let's draw a different picture for this. Here's water again, here is a sodium ion, and here's a chlorine ion. Oxygen, of course, is negative, hydrogen is positive, so you get a favorable interaction between hydrogen and chlorine, you get a favorable interaction between oxygen and sodium. So what actually happens is that when you throw the salt into water, it gets surrounded by water molecules. Oxygen, 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 all pointing at sodium, and you get the opposite for chlorine. Okay. So those are the different dipole interactions. And that will do it for Lecture 16. When we return, we will finish up with our discussion of non-bonding interactions by going over London dispersion forces.